So hello everyone, my name is Mustafa Baidon and in this presentation I will speak about Majorana fermions. So first of all, let us introduce our physicist, Ettore Majorana. He's a young Italian physicist. In 1937, he presented his final paper so what he did is that he was able to derive an alternative solution for Dirac relativistic wave equations, and those solutions were actually a revolution in physics simply because he solved them in terms of real wave functions. And that was actually extraordinary or a revolution in physics because he predicted that a particle could be its own antiparticle, and it was named after him, Majorana. And this was actually a really kind of revolution at his time. And after his final paper, he mysteriously disappeared. So he rode a ship or a boat towards Palermo just one year after his final paper, so in 1938. And in this ship and this boat, he disappeared. And up till today, his death is actually a mystery. And mystery, and 8 years after his 8 years after his final paper, we still don't know what is a Majorana, so his life is full of mystery. The particle he left for us and his mysterious disappearance. Um, so briefly, I will go through this outline. First of all, we will speak about the Dirac relativistic wave equations that Majorana himself added them or made an alternative solution for them, modified them, let's say. Then we'll start the search for Majoranas. So first of all, we're searching semiconductors, then we'll shift our search to our superconductors. Then I will speak about the Kitaev chain, so the system that will hoard Majorana fermions. At the end, I will describe the Majorana recipe. So the recipe for us to have experimental realization of nanowires, so how to actually build a system to measure nanowires. Now, first of all, a small short motivation. Why do we need to study about Majorana fermions? Now, as you all might know, that the shift nowadays is towards superconducting, building quantum computers, and those quantum computers are so they are built by Google, and Google is using superconducting qubits. However, Microsoft team is actually using Majorana fermions, so those particles that we are speaking about, Microsoft is using them to build such quantum computers. Why does Microsoft think that it's actually a smart idea? The reason is that they assume that if a system of Majoranas was built in terms of these superconducting qubits, in terms of these Majoranas, we'll have a quantum computer that's actually robust. So this quantum computer will be robust against any distortions. So a simple distortion will not kill those Majorana states. So that's why Microsoft is using Majorana fermions in building quantum computers. The second important reason is that we are speaking in physics about a particle that's spinless, has zero charge, a particle that's on antiparticle, and it has non-abelian statistics. So what does that mean? These properties are actually interesting for us to study. So what does non-abelian statistics very shortly is that it means that if we exchange this particle, we'll have a non-integer spin. So I kindly ask you to keep those properties in mind, because in our search for the Majorana fermions, we will see if the particle found matches all those properties, then we have found our Majorana. If one of those properties does not match, we will reject the assumed particle or the assumed group of particles that they represent a Majorana. So this is the map of physics. It was very famous when I was in high school. So as you can see here, I placed a star that represents the Majorana fermion. Now this star is actually will represent the Majorana fermions through all this presentation, so we'll always represent the Majorana fermion by a star. And I was actually subjective to place the Majorana fermions here under the condensed matter physics, because and through this presentation I will speak about Majorana's fermions limited to condensed matter physics and solid state physics. But actually the search for Majoranas for the past decade was also in high energy physics. So some research papers concluded were searching for Majorana's fermions as neutrinos. Even Majorana himself predicted that the Majorana fermion might be a neutrino. But I will speak. So I will prove to you why the field of condensed matter physics and solid state physics is actually a better place to search for Majoranas. Now here we study the Dirac relativistic wave equation. So this is the first Dirac relativistic wave equation. So in 1928, Dirac made a revolution in quantum physics where he studied such an equation. He wrote such an equation, and this equation made a revolution in physics because it predicted a new understanding of spin. If you look closely at this wave equation, we have a linear relation between momentum and energy, and here psi is made of 4 components, psi 1, psi 2, psi 3, psi 4, because we have a particle and antiparticle. So what Dirac did is that he predicted the existence of antiparticles using this equation. So in Dirac equation we had the field creating the particle, which is phi. So this phi represents a field creating a particle. Phi star is a field creating the antiparticle. And but in Dirac equation we never assume that these fields are equal. The second thing is that in Dirac equation, indeed, he did predict the existence of antiparticles. So using this Dirac equation, we had electrons, and he predicted that an antiparticle exists, for example, electrons and positrons. But he never assumed that there exists a field or a particle that's its own antiparticle. If we look closely at those matrices here in Dirac equation, you see that the entries of these matrices are sometimes complex and sometimes real. What Majorana did is that he modified the Dirac relativistic equation, or let's say he found an alternative solution where the following follows. So he found an alternative solution where we have those matrices, and those solutions for those Majorana fermions are always in terms of complex numbers. So as you see, the entries of those Majorana matrices in red are all complex numbers. So this is the Majorana equation. This means I complex number times those matrices is a real. This means we have a real wave function satisfying the following. In Majorana equation, we assume that the field creating the particle and creating the antiparticle is the same. What does that mean? That means that the particle is its own antiparticle. This can only be true if it's spinless and has zero charge. Remember those 4 properties? They come again here. So this satisfying gamma is equal to gamma dagger. So the creation and annihilation operator of a Majorana fermion are equal to each other. I'll use gamma for Majorana fermions and C, G dagger, and CG for electrons. Now, if I had the chance to open the floor for guesses, I think a smart guess would say, what is a Majorana fermion? Some of you would guess that it's an exciton. So this is a scheme of an exciton here, if you forgot. Here you have a conduction band, a valence band, an electron and a hole, and there is an electrostatic bound state between this electron and hole, and this forms a zero charge. So actually, indeed, an exciton is a smart guess that it is a Majorana fermion. However, I will prove why it is wrong. So the first smart guess in solid state physics and the most straightforward guess is that it's an exciton. So why is it wrong? We'll use the language of second quantization. Here we have this creation operator and this annihilation operator. And using the first basic law in Fermi-Dirac statistics, we have Cg dagger squared is equal to Cg squared is equal to 0. This means 2 particles or 2 fermions cannot occupy the same state. That being said, I can now I can now represent for you the exciton relation in second quantization. So this is the formula here. This means that they are bosons with integer spin. Remember those properties. They have non-abelian statistics. What does that mean? They don't have integer spin, and this is actually not the case for an exciton. So we reject the assumption that an exciton is a Majorana fermion because a Majorana fermion has non-abelian statistics, but an exciton has is a boson with integer spin. Now we are looking for something like the balls here, the two red balls here. So we are looking for something like a half a particle in white and half a hole in red. So we're looking for such thing because an exciton is actually two distinct particles, electron and a hole. But what a Majorana fermion is actually half a particle, half a hole. Okay, I think I should stop.